Right, welcome to this our CAWASA Wednesday webinar. This is number 15 for 2025. And today we've got a special guest who is going to be speaking on the introduction to stormwater. He has spent the past 25 years in the stormwater industry. Most of that time has been in product development, and he has co-authored 6 patents. He has been active in standards development, working with ASTM, STEPP, and Canadian ETV program. Prior to getting into stormwater, he worked at Trojan Technologies, a water treatment equipment manufacturer. His focus there was on drinking water purification using UV peroxide. So to lead us through the topic of introduction to stormwater, I'd like to welcome our special guest this afternoon, who is Dr. Gregg Williams. And I would like to thank the Operators Without Borders for finding us Dr. Williams. Welcome on board, Dr. Williams. Over to you.
Thank you very much. Thank you for having me. I appreciate the opportunity to talk to this group. I realize that stormwater is not exactly up your alley, so I will try to kind of keep it some general stuff that applies to non-stormwater. I realized as I was making the presentation that I was getting really probably too deep into it. So I tried to pull back a little, keep it high level, and hopefully it'll be information that everybody finds useful. So I'm going to, I did put together
Yeah, you have permission to
a presentation.
share slides. All right.
All right, so I haven't done a lot of Zoom sharing before. Let me just see. It says I'm paused.
It says you should double click to enter full screen mode.
Oh, okay, where am I? Let me go back to share. Full screen. Oh, hang on. Okay, I've got that open now.
Right.
Just find my slides. There they are.
There we are.
Okay.
And you've got, now I'll go to the slideshow.
You can see that now?
Yeah.
Okay. So I'll go to the
slideshow.
here we go.
Yeah.
All right. Thanks, everybody. Sorry about the technical glitch there. It took me a second to get rolling, but here we go. So I'm going to talk about stormwater and stormwater management today in particular. And with stormwater management, you'll notice I've tended to do things in pairs, or in the case of the R's, there's 4 of them. So I kind of try to keep a theme. So for the stormwater management, the 2 things we're going to look at are quality and quantity. And then the 4 R's of stormwater that I like to talk about are rainfall, runoff, removal, and resilience. And then there's going to be subcategories of all those, but I'm going to kind of step through those over the next 15 minutes or so. So, I mean, really, at the very basic level, stormwater management's about quantity and quality. And the 2 are different enough that I think it's worth separating them out. So I do talk about each of them. And so for stormwater quantity, that's what gets all the press. You know, stormwater quality, you get hurricanes, which lead to flood, you get droughts. You know, when there's too much water or not enough water, it gets people's attention. There is a more kind of subtle problem. You can have some stream bank erosion can be an issue with quantity. So there are a bunch of reasons why you want to control the amount of water that you've got going into your treatment systems or your sewers at any given time. And so if you're going to design for quantity, you really want to consider my first 2 R's. You really have to think about rainfall and runoff, which are very related. And these days, it makes sense to consider that 4th R, that resilience piece. I think it's pretty widely agreed that for whatever reason, rainfall patterns are starting to change. And, when we design stormwater control measures or really any kind of water treatment, the projects tend to have very long lifetimes, 20, 50 years, something like that. And so, if rainfall is going to be changing, then there's a chance that something that we design today won't still be working near the end of its life. And that's not what we want. So that's why it's useful to start considering this fourth R resilience. Now, one of the things about quantity that's a little different from quality is, when you're designing for quantity, you want the large events are what you worry about. And you worry about large areas. So, you don't want to flood a neighborhood. You don't want to destroy a riverbank. And you'll see in a couple slides, quality, it's a little bit different. But I'm going to stick with quantity for just a second, a couple more slides. So usually the way this has been done in the past is with gray infrastructure. So sewer pipes, underground detention tanks, concrete structures that you build to move the flow where you want it to go. More recently, there have been some advances in what people call green infrastructure. Sometimes it's also called LID, which stands for low impact development. And here what you're trying to do is sort of mimic some of the infiltration that you had prior to development so that your rain doesn't get off your site and into your sewer system. So you kind of try and control that quantity at the source. Of course, there's always trade-offs with these sort of things. If you when it comes to quantity, the trade-off is capacity and cost. If you want to design to handle a really large storm, like your 90 inches an hour, a system that can handle that is basically never going to flood because that 90-inch an hour storm is going to happen once every 1,000 years. And actually, not exactly, and I'll get into that in a bit, but it's kind of what people would call a 1,000-year storm. So that system is great, very safe, never floods, but it would be massive. The pipes would be huge, and therefore it'd be terribly expensive. On the other hand, you could design a system to handle, a much smaller, like 2-inch an hour storm, and would be a manageable system. Wouldn't cost a whole lot of money, but it would flood on average every couple of years, and that has sort of additional kind of unforeseen, difficult to calculate costs. So there's always this kind of cost and capacity trade-off when you're looking at quantity. Now, quality, which is more my specialty, is important because stormwater is a significant contributor to water body impairment. It will because what it does is it transports pollutants, sediment, trash, nutrients, metals, even heat can be thought of as a pollutant. Stormwater will transport these things off the land into receiving bodies, and they can be a problem there. So, and it's something that you don't really necessarily think of. A lot of times, people when they think of pollution, they might think of something coming out of a water treatment plant or coming out of off an industrial site, with a big pipe with a bunch of crud pouring into the river. But actually, often it's stormwater is just runoff, and it's a non-point source. It's much harder to identify, so it can be tricky. And so, managing the quality of stormwater is also an important consideration. Unfortunately, designing for water quality is a little bit more important because you need all four. Well, you need the first 3 R's for sure. So you need your runoff, your rainfall, your runoff, and your removal now. And again, you should consider this resilience, this fourth R, because these systems are also tend to be designed for sort of 20 to 50 years. And then complicating it is there's maybe multiple pollutants of interest. So when you're worried about quantity, all you're worried about is water. When you're worried about quality, you're worried about what's in the water, and that can be a long list potentially. So unlike quantity, where you're really worried about the large rare events, here you're more interested in the smaller, more frequent events, and you're looking at smaller areas, something like a parking lot. So the scale of the two is different, and so the approaches you need for each of them is also a little bit different. And so when you're managing quality, there's really kind of two main processes that people use. There's sedimentation and filtration. Sedimentation is basically gravity settling, where you let particles settle out. You give them time to fall out of the water. Filtration is more, well, filtration. You actually physically stop the particles from passing the filter. And like quantity, there are green and gray options for both of these. A green option for sedimentation would be a pond, something that's that's been traditionally used. Lots of those around. More recent, probably within the past 30 odd years now, you get hydrodynamic separators, also called gravity settling devices. In Canada, we call them oil grit separators. They're all the same thing. It's a manufactured device that tries to control the water movement to maximize the time it spends and kind of minimize the footprint. Because ponds work really well, but they tend to be large. And then in terms of filtration, again, a gray option, or a green option would be a swale, and a gray option would be a cartridge filter vault. So you'd have a concrete vault, and then you'd have a bunch of filters in them with cartridges that would be filled with media. So again, trade-offs, it's like everything requires a trade-off between cost and quality. The larger systems tend to work better. They also tend to cost more, as with quantity. With quality, again, there's this extra little wrinkle. You have this maintenance issue. With quantity, you're really looking at pipes and tanks, and they don't tend to need a lot of maintenance over the course of their lifetime. But with a quality system, a water quality system, they all they all capture the pollutants that they're removing, which means the pollutants build up inside the system. So you have to clean them out periodically, or they'll get full and stop working. So there is that extra kind of life cycle cost. And the kind of that other trade-off is the better the system works, the more it's going to capture, the more maintenance it's going to need. So you hear people talking about a maintenance-free system. A maintenance-free system doesn't work. So good news and bad news. Good news is it's cheap. Bad news is it's not doing anything. Okay, so into the 4R. So that's kind of some of the ideas behind why we do water quality management, some of the really basic concepts. Now I'm going to get into these 4Rs, and then these first couple I think are relevant even if you're not in the stormwater game, because chances are, I mean, less so for drinking water maybe, but for wastewater treatment, you probably receive rainfall in your treatment plant, right? And so kind of understanding rainfall can help you understand some of these excess flows that are going to potentially cause problems in your process. Because rainfall, it's the same, it impacts stormwater management and wastewater management in the same way. So the data that I'm gonna be showing, there's not a ton of it, but I took it from the NOAA, which is the National Oceanic and Atmospheric Association, PFDS. And the PFDS is their precipitation frequency data server. I put the link there for you. It's all the data that's on there. So it's basically, it gives you like tables and graphs of data that can be found in the NOAA Atlas 14. It's an amazing resource. The weakness is that it only covers the US, Puerto Rico, and the US Virgin Islands. So it may not apply in your areas. I would expect that there are similar types of resources, kind of rainfall data collections in the Caribbean, but I haven't had a chance to research them, so I'm afraid I don't know exactly where they would be. So that's why I'm using the NOAA stuff, but the concept is exactly the same. So one of the things that you get from NOAA and that you need in kind of understanding rainfall is it's something called a DDF, or a depth duration frequency curve. And it's basically a way of telling you how often you can expect to see a storm of a certain size. And so I've got this crazy example. This graph is actually from Puerto Rico, and I picked an example that's not very practical, but it's very easy to see. You can see here that this line is the 1,000-year storm. And so you could see that, once every 1,000 years, according to this graph, you should get a storm that lasts 3 days and drops 30 inches of rain on you. So another way of looking at that, and so keep that in mind. Another way of looking at that, one that's kind of more common in stormwater, is actually an intensity duration frequency curve, an IDF curve. And this tells you how fast it is raining, because that's actually a little more problem. That's more what you're worried about when you're trying to design the size of the system. Because you remember, I talked about that that 3 day the 3 day storm, the 3 day 1,000-year storm. So it dropped 30 inches of rainfall, which sounds like a lot, but it was over 3 days. And so that actually only works out to, if you look at it on this graph, it's only about 0.6 inches per hour. So 0.6 inches per hour is a lot. I mean, 30 inches over 3 days is a lot, but it's not terrible, probably manageable. On the other hand, if you look at something like your 1,000-year 10-minute storm, that's 90 inches of rainfall. So even though the total amount of rainfall might not be much, it's coming down so fast, you're going to get a lot of runoff and a lot of impact on your systems. And so that's why I think people tend to use these IDF curves when they're trying to size their systems and understand how much rain they're actually going to have to deal with. So kind of a quick warning. I said that the PFDS is a fantastic source of data, and it is. It has all these IDF curves. The one problem with them is that they use rainfall data generally up to the mid 2000s, maybe the 2010s. So any sizing you do based on that data is already 10 to 20 years out of date. And so if we acknowledge that, rainfall is changing and generally getting more, sizing based on that stuff, based on the data that you can find, is already a little bit out of date. So you have to start to make some compensations just for that. And for example, I did double check, and the Puerto Rico and US Virgin Island data is actually from 2022. So it's 23 years old. So anything you size based on that is probably too small when you install it, let alone when it reaches the end of life. Now, people know this, and so it has been addressed. There's something called Atlas 15, which was going to be an update of Atlas 14. It was going to include updated rainfall data. It was also going to include some of the resilience modifications or resilience compensations that I'm going to talk about in a few slides. Unfortunately, it was kind of delayed, maybe canceled. So I'm not sure if we can really rely on getting Atlas 15 anytime soon, which is too bad, because there are lots of ways to account for resilience, but there isn't. It'd be nice to have Atlas 15 that would be kind of a central methodology, right? Because right now I'm going to present 3 different methods, and there's no way of knowing whether one is better than the other or not. And it would have been nice to have some guidance from Atlas 15, but it's, we'll just have to wait. Okay, and I do want to address that 1,000-year storm that I mentioned, because you'll hear it. I only picked 1,000-year because it was easy to use on the graph. You don't really hear that very often, but you'll hear a 100-year storm in the news reasonably often these days. And what a 100-year storm means is it's technically, that's the return interval. And when people hear that, they think, oh, that's just a storm that happens once in 100 years. But what it really means is that return interval is actually a probability. You flip that upside down, and if it's a storm that happens once in 100 years, has a probability of 0.1 of 1%. So my 1,000-year storm has a probability of 0.1%. So it's confusing because people, it's a natural tendency. If you hear, oh, there was a 1,000-year storm yesterday, that means there won't be another storm for 1,000 years. But probability doesn't actually work that way. What it means is there's a 0.1% chance of a 1,000-year storm every single day, right? So just because you had one yesterday doesn't mean you won't have one tomorrow. They're independent events, and that can be confusing for people. So be a little careful. And there's a couple other reasons, but bottom line is you can reasonably expect to hear about 2, 3, 4, 5, 6 100-year storms in your lifetime, when really you should only hear about one, right? If you live to be 100, you should experience one 100-year storm. chances are you'll do more than that. And again, it gets complicated by the fact that the rainfall is changing, and so it's changing what a 100-year storm is, it's not a 100-year storm anymore. Okay, so that was kind of an introduction to rainfall. I talked about rainfall and sizing for rainfall, but what we're really sizing for is runoff. Because rain that kind of, if rain falls in the forest, do we have to worry about it? And the answer there is no, because it will fall in the forest and it will stay there. It'll infiltrate into the ground and into the water table, and it'll be fine. It only becomes a problem when it hits something impervious and turns into runoff, which you can see in this picture. So I talked ahead of myself, so here it is on the slide. What we're talking, you usually hear about design storms and intensities, but really what you want to know is when you're designing a pipe or a HDS or anything, is what the flow is, what the runoff is. And they are related. More rain will mean more runoff, but they're definitely not the same. There are factors that impact how much of your rain ends up getting turned into runoff. And so I have a quick discussion on this as well. I mean, there are a lot of ways to model runoff. So if you have rainfall data, which we have lots of, there are ways to turn that into runoff data. Computer programs are often used. or SWIM, which is the stormwater management model, was developed by EPA. It is a good way to calculate runoff. It's kind of beyond the scope of this, so I'll just tell you that exists. You'll also hear names like HEC-RAS and other things, and some consultants have kind of proprietary models, and their whole job is to turn rainfall into runoff. And they actually, most of them are based on some of these manual calculations, like the rational method or the NCRS curve number method. And so because those aren't complicated computer programs, I'm going to talk about them a little bit. I'm also going to talk about this next level version of calculating runoff, which is a probabilistic rational method. So you can see the traditional rational method on the left and the probabilistic rational method on the right. And all it does is, so it converts your flow rate Q is based on a coefficient that you get out of a table, intensity, and how big the site is. So it makes sense, right? It's kind of intuitive. As higher intensity equals more rainfall equals more runoff, and a bigger site means you get more rainfall on a bigger area, so it's going to also equal more runoff. And the only change when you go to the probabilistic rational method is that it recognizes that flow kind of increases with the depth. So the size of your storm actually impacts this rational method coefficient. So it brings in a probability and makes your predicted runoff from a given storm a little bit larger. But yeah, so that's kind of a quick way. You'll hear about the rational method still being used. It was invented in like 1850s and still gets used to calculate runoff to this day. And that's basically what's going on. The probabilistic rational method is what SWIM uses and most of the computer programs. And it's a better, it's one of those things where now that we know that we can do better, we probably should do better and move to that method, but it hasn't been universally adopted yet. But that's all I'm going to say for now about runoff, because again, it's one of the all these topics get really complicated really fast, and I'm going to try to stay away from that. So I'm going to move right on to removal. And removal is water quality specific. So those last two really impacted kind of predicting how much water you're going to deal with. Removal really talks about how you're going to deal with smaller amounts of water and how you're going to reduce their impact on your receiving waters. In most situations, sediment is the primary cause or primary pollutant of concern. It has a bunch of negative impacts. If you dump sediment into a river, it's bad in and of itself because it causes problems for aquatic wildlife, and it can disrupt sunlight penetration and just kind of generally throw off the ecosystem. Sediment also often comes with pollutants bound to it. So you get chemical contaminants along with your sediment. So a lot of focus is on moving sediment, but there are other pollutants that can be addressed independently, and I'll talk about that. So your two removal mechanisms, getting back into pairs again, are sedimentation and filtration. I already introduced those, and I talked about hydrodynamic separators. So they use gravity to remove particles and any particle-bound contaminants. And then filtration, you've got vaults with some kind of media in them, like a sand. So, a sand filter is a water quality device. It provides you with filtration. And what you can do with filtration is if you add a kind of a chemically active media, like you could do something like an iron enhanced sand, and that will actually give you pollutant removal beyond whatever's bound to your particles. So iron enhanced sand happens to be good for phosphorus. So if you're worried about phosphorus runoff getting into your lakes and causing eutrophication, well, one way you could try to control that would be through an iron enhanced sand filter. So removal models, I started getting into modeling, which is something that I do a fair bit of for work. And I realized it was going to get way too complicated. So I kind of tried to pull it back. And so I'm going to address it a little bit. And, it's one of those things where if anybody wants to follow up, I'm always kind of happy to dig deeper, but I don't want to get bogged down right now. So I'm just going to say high level. I'm going to talk about, these basic removal models. Both sedimentation and filtration are very difficult to model. So they're the state of the art. Like, so when people are designing for these systems, they're using empirical data, right? So there isn't a good mathematical model for removal. So they use this, they run tests and just determine, hey, how does this system perform? And then you can use that data to make predictions. There's two good sources of information on removal. There's the New Jersey Department of Environmental Protection program that they run through NJCAT, which is New Jersey Center for Advanced Technology. And NJCAT has a database that has data on removal versus flow for HDS and filters, and it's all lab generated data, so it's all relatively clean and easy to work with. Another source, if you want field data, is the Washington Tape program. It only really has filters, aren't really any HDS in the tape program. And field data, it has this advantage. People like field data because it's more real. The problem is it's also more dirty. It's really hard to it's hard to understand and process field data because there's so many kind of what ifs and caveats and stuff. So it's more difficult to use field data than lab data. So, but it's all there, and those are two good sources if you want to kind of get started. At least they give you a starting point. So, so two things to watch for when you're looking at removal models and trying to figure out what kind of removal you're going to get from a given system are the PSD, the particle size distribution, and the flow. And chances are that the PSD and flow used for the New Jersey test or for the Washington that they got in the Washington field site don't look anything like the PSD that you have at your site, PSD and flow. So you have to do kind of a translation, right, to get that data that's existing on the web and make it so it's more useful for your site. There's no kind of common way to do that. There's people that have different ideas, but there's nothing that's kind of really generally accepted. So, I mean, one thing, there's the ASTM, the ASTM International, which is a standards organization. They're working on some guidance for how you can take PSD and flow and take one set of data and modify it for another set of data. The flow is actually relatively easy. there should be a standard methodology for that available probably next year through ASTM. PSD is a little trickier. It's going to take longer to develop a standard methodology for that. I do have a method that I use, and I recognize that it's the error in removal when you go from one PSD to another is probably like 10 to 20%, which is pretty large, but is better than nothing, right? So that's kind of the justification for that. So that's something to kind of the two things that really matter if you're ever thinking about installing a water quality device, you need to know the PSD and the flow. So again, I'm going to kind of leave it there before we get too far into the weeds. And I'm going to move on to the resilience piece. And so, at this point, it's commonly accepted and widely known that rainfall is changing. Exactly how it's changing is less clear, and what to do about it is also less clear. And it's difficult for us in the water quality world, which is where I mostly live, because the focus on changing rainfall is really these kind of global climate models and flooding. So it's really this large scale changes. And so a lot of advances have been made. There are numerous climate change models now that predict what will happen in scenarios. There's all kinds of ways of predicting what might happen with your rainfall. But it really only applies at this large scale. When you get down to a small, an acre, 1 acre parking lot or whatever, the global models start to break down at that point. There isn't a good way to take this relatively good prediction, this is what's going to happen over the whole world for the next 20 years, and turn that into this is what's going to happen on my site in the next 20 years. And so that's an ongoing challenge for the stormwater community. So, you'll hear a lot of work is being done on, call it global warming, climate change, whatever, resilience. A lot of work is being done, but it doesn't all apply to us because it's more for the quantity people. So that's just kind of my pitch for doing more studies on small scale climate or small scale resilience. Okay, so we're getting back on track here. So the challenge is really kind of predicting how rainfall is going to change, and then how those changes are going to impact a specific site. So, what kind of runoff is that new rainfall going to turn into? And in the past, we just used the NOAA data as is, and we assumed something called stationarity. And stationarity in words is a stationary process, also called a strictly stationary process, is a stochastic process whose statistical properties such as mean and variance do not change over time. What does that mean? Well, it's easier to understand in a picture, which is worth 10,000 words. So this is some IDF curves again. And it doesn't look exactly like the previous IDF curve, which I showed you. I showed you these. And the difference is that here, this has a logarithmic scale. So it goes from 0.01 up to 10. And by doing that, it kind of straightens out the curve, because this is much more common here. Again, you still got your intensity and your duration, but now it's a linear scale, so you start to get that curve. And what you're seeing, and here, instead of putting all the curves, so on this graph, it's got everything from the 1 year to the 1,000-year return interval. On these graphs, it splits it out. It only goes 2 to 100, but it puts them each on their separate graph because it kind of shows you the effect of non-stationarity. So stationarity, simply put, means we expect the rainfall in the future to be the same as the rainfall in the past, right? So that's those black IDF curves. That's what was happening in the past. Non-stationarity means, well, the rainfall in the future is going to be different. And this is actually, actual data that people analyzed. And so these IDF curves, you can see the red curves are all higher than the black curves. So, for example, your 2-year storm, which has a 50% chance of happening on any given day, a 1-hour storm is going to go from 15 millimeters an hour to 25 millimeters an hour, which is significant. So you're going to see a lot more of these storms and a lot more stress on your stormwater management systems. And you can see that it varies depending on the return period. The last thing on the graph is the uncertainty in this non-stationarity, and so that's another thing we kind of have to deal with, and it's something that does get recognized. If you look at the NOAA data, they do publish confidence limits. So they publish the 95% confidence limit. So they say, we're 95% sure that the data is going to be between here and here, and then they draw the line here. So that's kind of what this red line shows. It's like, well, this is the average that we expect, the average change that we expect, but there's a 5% chance it'll be this high and a 5% chance it'll be this low, right? And so in addition to kind of this rainfall increasing, the uncertainty is also increasing. So it does make it complicated, quite a bit more complicated now when we're trying to figure out how to size for the lifetime of these products, going into the future. And as I said earlier, even now, because we now know that the rainfall, a lot of the rainfall data we're working with is 20 years old, so it's already out of date. And so, our 2-year storm probably isn't this anymore. It's probably somewhere up in here. Um, so that's changes in stationarity and kind of how it complicates the whole sizing process. Here's the old IDF curve that I just brought back for comparison. So I'm going to talk about some current adaptations. So there are three kind of things three things that I've heard about that people are starting to use. So one of them is shifting the return period. So, a concept that people often use when they're designing systems or creating regulations is the design storm. So I'll go back to New Jersey because they're active in the whole stormwater management regulation space. And they have a design storm. So they say your system has to be able to remove 50% of the sediment from the 2-year design storm, basically. So, which is really, and that makes the sizing process relatively easy when you have a design storm to work with. But changing the design storms, in regulations, it can be difficult. In New Jersey, it requires new legislation, so shifting it is hard. But at least the concept is kind of the same, and so you can make this adaptation and say, well, I know my rainfall is getting worse, so I'm going to see this 10-year storm, this bigger storm, more often. So maybe it becomes my 1-year storm, maybe it becomes my design storm, right? So that's one way to adapt. You'll end up sizing bigger systems, but they'll last longer. They won't fail as soon. The problem with that again is kind of there isn't at this point there isn't like a defined, hey, you should change your 1-year to your 10-year. That's up in the air as to what the right shift would be. Another thing that people are doing is using only more recent data. So, and I meant to do a graph of this, but one of the things with the non-stationarity is kind of your peak rainfall is increasing, right? So it's kind of going up like this. And what happens is, because our data is really old, so it has a long flat tail. So some of this data in NOAA goes back to the 1930s, right? And so if you use all that data, the flat tail is going to dominate the recent uptick, and you're going to get a lower predicted change, right? And so what some people are doing is they're saying, hey, what's really relevant is this new uptick, And so if I only look at the last 20 years of data, for example, I'm going to have a bigger change predicted than if I looked at the last 100 years. The problem with that is if you use less data, again, you increase the uncertainty in the model. So that's one of the reasons people use 100 years worth of data. It's just kind of a reality of statistics. The more numbers you have, the more data you have, the lower your uncertainty is going to be. So you can narrow those gaps, these confidence intervals. So that's another adaptation. You can use only more recent data. And lastly, I said 95. I wrote 90. Now I can't remember whether NOAA publishes the 90 or the 95. Got to be honest. But one of those two. But what you could do is instead of using the NOAA line, you could use that upper confidence interval. So again, you're going to get a bigger system that's going to last longer. The problem with that adaptation is, the data is outdated. So the confidence that even that higher line is also outdated. And I do have some examples of these. Adaptation number one. So this shifting the return period is kind of what New Jersey has done. And so they actually changed their sizing to a 10-year storm from, I think it was a 2-year, not a 1-year. And that result is intended to be conservative. Again, building bigger systems that are going to last longer. It does actually, when you plug it all the way through into a removal model, it is probably slightly aggressive for current conditions. So it's not really giving them the adaptation that they want. So, but it's what they have for now. That's one of the realities is, when there's no right way to do things, you kind of have to make a best effort, right? And so this is the best effort that they've landed on. This adaptation number two, Connecticut was an example. So they're using more recent rainfall data. So you can see they changed their design storm from a 1-inch storm to a 1.3-inch storm. The 1-inch storm was based on data back to the 30s-ish, 20s or 30s. And the 3-inch storm was based on only using data from the 70s. The 1.3-inch storm was based on only using data from the 70s. So you get this 30% increase in rainfall, which gives you basically a 30% increase in flow. And then using the rational method, and then using something called a net annual sizing method, which includes the probabilistic rational method, you get a 36% increase in flow. Those numbers are kind of left over from my more detailed presentation, so don't worry about that. The bottom line is, just by shifting, they're looking at the same rainfall record, but by only looking at the recent bits instead of the whole thing, it increases their design storm by 30%. Is it the right thing to do? Not sure, but again, it's certainly better than nothing, and it's kind of a best effort. And then the third adaptation, I brought them up because they do exist in the wild. There's some areas that are considering using the upper confidence level. Massachusetts is, I believe, looking at that, but I don't think anyone's actually implemented it yet. So these adaptations are kind of out there. But as I mentioned, it's a bit of a Wild West. There isn't a real authority. There isn't a good sort of scientific reason, hey, this is how it should be. This is the adaptation you should use. So it's still a little bit up in the open. Now there is a more resilient adaptation, and I think this is something that that NOAA was kind of planning to put into Atlas 15. So it may yet come back, but for now, I'm just going to kind of throw it out there. This is actually what StormTrap uses. So again, if you wanted to get into detail, I could go into lots of detail on that. But I'm just going to throw it out there for now as kind of, if you come across someone who's using what's called a net annual sizing model, that's really, that's a best practice for current sizing. And this net annual sizing model has an advantage, is it's fairly easy to update to account for resilience. Sizing model has a rainfall piece that has 2 or 3 parameters that can kind of be adjusted Just like you're adjusting the parameters A, B, and C in a linear regression model, you get y equals mx plus b. So your line, m is your slope, goes up and down, and b is where it intercepts. Rainfall is much more complicated to model than just a line, but it's the same idea. It's got a couple different parameters, and you can adjust them to account for changes in rainfall. And then the net annual sizing model also lends itself easily to this probabilistic runoff, so it's adaptable. And so you can change your rainfall and your runoff to adapt for climate change, and then you just plug the removal model in, because the removal doesn't care where the flow comes from, it just cares how much flow there is, right? So as that changes, the removal model isn't independently impacted by climate change. It's only impacted insofar as there's more runoff. All right, so that was what I had. I wanted to thank all of you for sticking with me. I was aiming for about 45 minutes. I hit it. I have time for questions, so feel free to ask questions now. I guess you can put them in the chat, or I don't know how you want to handle that. And I will leave my contact information for people.
Thank you so much, Dr. Williams. That has been a very good introduction to stormwater, as this is not very common in our parts, albeit that these days, with a change in climate, we are seeing increasing challenges with managing stormwater, with a lot of flash flooding in many of our cities across the Caribbean. So I think it is a good perspective, and we can understand some of the, or you have given us some good pointers, or some points of departure where we can dig deeper into at some future period. So I will now open the floor for some of us who are participating to field questions, to ask questions, or post them in the chat as you directed. We'd like to acknowledge the presence of Valerie Jenkinson, who has helped us in coordinating this activity, and to wish her well. Yeah, but I noticed. Well, of course, you spoke of some of the some of the methods. You referred to the rainfall, uncertainty, climate change, and about data. And of course, within the Caribbean, we also have we rely on a lot of collaboration with NOAA through the Caribbean Institute for Meteorology and Hydrology based in Barbados. Okay. But one of the things that came up was I think you spoke about a 30% increase in rainfall may lead to the 36% increase in flow. How extensive in terms of say preparedness for managing in the context of climate change? How well does that prediction help with your preparation for managing your stormwater systems?
Well, it's really critical, because your stormwater systems are all sized to handle a certain flow. At a very basic level, your pipe needs to be big enough to convey all that flow without backing up and flooding manholes, all sorts of things. So the pipe diameter you choose will be directly related to the amount of flow you expect to get. And the difference between 36% more flow and 30% more flow is not too critical, but the difference between no flow and 30% more flow is certainly significant. And so that's kind of, when you look at these adaptations, it's maybe not important to get hung up on exactly what you do, as long as you do something. And the missing piece is something that I'm interested in, is trying to balance risk reward, right? And so what you do is you would try to get some estimate of the cost of flooding, for example, and then and match that up with the probability of flooding, and that becomes a risk number. And then you can compare that cost of flooding times the probability. You can compare that to the cost of building a bigger sewer system. And so you can do a calculation that says, hey, I may, if I spend money now, I will end up saving money over the long run, over the life of the project, which is, what you want to do. So it becomes a kind of a life cycle analysis. And the principle is very easy. The trick is always, how do you get that risk number? So how often are you going to get floods? That changing piece is the one that people aren't really agreed upon. And uh, so that makes it challenging to do those calculations. But you saw the examples. A lot of places are doing at least some kind of adaptation. So they're sizing stuff bigger and hoping, it's like, that should reduce our risk as best we can.
Yeah, I imagine that would have some of those critical risk analysis would be considered where in more so in some of the low-lying states and in the riverine areas where that are very highly at risk for flooding and putting in your dams and berms, etc.
Right. And that's actually, from a flooding point of view, I think the situation is better than it is for the water quality point of view, because the flooding predictions that you get out of global climate models, if you're looking at a flood over an area of many square miles or kilometers, you can get actually a decent prediction of that from a GCM. And uh, flooding, in terms of calculating flood costs, that information is getting better and better as well. So I think there are resources out there where if flooding was the main concern, you really could get a good idea of kind of the cost benefit. And sure, some of it is berms, and some of it is bigger pipe, some of it is separating your CSOs, separating your storm sewers and your sanitary sewers, that kind of stuff. So yeah, the numbers for that are not so bad. The numbers for water quality are a lot trickier. Again, because it's smaller scale, predicting the future is a little bit harder, and quantifying it is also more difficult. It's like, you can say, hey, if I flood a house, it's going to cost this much to get the house. But you say, hey, if I flood a stream and kill all the fish, what's that worth? So lots
Yeah.
of uncertainty.
I've got a question from Valerie, and I think I think Don Vlugman after.
Yeah,
Over to you, Valerie.
thank you very much, Greg. Very interesting. I noticed that I know in Canada there is a number of utilities that are now putting a third tier onto their tariffs, their rates and tariffs, and they're having water, wastewater, and stormwater tariffs. I wonder because this is a problem in the Caribbean where we don't have increases in tariffs for many, many, many years. So I think that this is a long time off. But are you seeing a growing trend in this?
Oh, absolutely. Yeah, there's wide recognition in North America, the US and Canada, that infrastructure is under stormwater infrastructure is underfunded. The American Society of Civil Engineers, the ASCE, puts out an infrastructure report card every year, and stormwater always gets a D. And it just means because it's one of those things that hasn't, we built all our sewers 75 years ago and then forgot about them, and in part because there is no funding for them. So yeah, that's been recognized as a gap, and we are starting to see stormwater utilities. Yeah, I have one in the town that I live in, and yeah, I mean it's a good way. It's a good way to do it because it's difficult. There are funding mechanisms for water treatment in general, wastewater, drinking water. But stormwater is always kind of considered less important. So it has a really hard time carving any of that funding out. So for example, in the US, they have what are called state revolving funds that are supposed to supply funding for infrastructure. And in theory, they should include stormwater infrastructure, but in practice, it never does. So, having an independent kind of stable source of funds is extremely important for the future.
Right. Tom Blugman, over to you.
Yeah, good evening, good afternoon. It was a very, very interesting presentation. One of my favorite subjects, storm drainage. But in the Caribbean, we have separate sewer and storm drainage because we don't have combined systems like in the more temperate climates, because we have serious storms or rainfall.
Right.
Our intensity, duration, frequency curve start at 250, 300 millimeters per hour.
Yeah.
That's about 10 times or multiple times your charge. So we keep them separate.
Yep.
But also, and I do know the latest developments, but I know that the Caribbean CMIH, Institute for Meteorology and Hydrology, did some review of the IDF curves that were being used in the Caribbean, and they called outdated. They were from 50 years ago, with a 30, 50-year history. And they also agreed that we need to update them to actually capture the impacts of climate change, which in the Caribbean is in some areas higher rainfall and in some areas lower. But when it rains, it pours. So the intensity might increase. So that these are and I do not know, and maybe one of the participants knows, uses these IDFs and has update on that. I do not know the update for that, but I think that's critical. And I also think that more attention should be paid to proper stormwater drainage. And I also involved in emergency response, and I see a lot of floods after hurricanes or storms. Not even hurricane, a tropical depression might cause significant flooding because the drainage is not working. Or a road is being constructed, but the road is on a dike, and the dike acts as a dike.
Yeah.
and the culverts are too small and they get blocked. So I think it needs much more attention to be paid to this. But I'm inviting other participants who are involved in road drainage or urban drainage, and also our collection area, catchment area, is much bigger than the city. It comes from also upstreams in the hills. A lot of water comes down, so it's not only the urban developments, but also the landscape around it that drains into urban developments. But I'm asking participants if they have any insights in the recently used IDFs in the area. But thank you very much for your very interesting presentation. I will go and check out the websites you give.
Yeah, you're very welcome. Yeah, the rainfall, you raise a good point. One of the impacts is it does seem to be getting peakier. So you're getting kind of shorter, more intense storms where it's happening. So you may not be getting an increase in total rainfall, but you're getting it faster, which has an impact on drainage and design. And and you also raised a good point about the size of your catchment area. In your kind of rainfall where you have high intensity storms, you can't actually count on the undeveloped area infiltrating everything, and so you will get rain even from pervious surfaces contributing. So yeah, it's a different challenge. It's the same concept, but you have to think about a few more things.
Right. Are there any questions, observations, comments you wish to make in the audience? I'm not seeing any questions in the chat.
Hi, good afternoon. I hope you can hear me.
Yes, please proceed, Augustus.
Yes, Timothy Augustus here, professional operator out of Trinidad and Tobago. Is it that you would also make what you call recommendations to those developers who are putting down houses, malls, cities, towns, in terms of having concrete and roof areas throughout their compound, which of course would contribute to where the water ends up. The other thing is deforestation. You have unplanned developments and so on. Like what our city in Port of Spain here, we had a functional water retention pond, but I don't know, it seems that that has just deteriorated and we are back to having the slightest rainfall, the city floods. So my question is really, you know, is there a way to, or do you also contribute to adding those type of recommendations to some of those developers or even countries?
Yeah, I mean that's an important that's a part I didn't touch on because it's not really introductory. Is the whole idea of a sizing model, you know? So if somebody's building developing, say they're developing a Walmart, right? So it's going to be a big roof, it's going to be a big parking lot, there's going to be a lot of impervious area. You know, how they determine, like how they predict what the runoff from that site is going to be is important in terms of sizing all the downstream piping and stuff. And so it's good to know, you know, if possible, to find out how they're doing that. So, you know, because basically this, because what we call a sizing model includes all those considerations. So sizing model is going to account, it's going to have a way of calculating rainfall, it's going to have a way of calculating runoff, it's going to weigh, if it's a water quality model, it'll have a removal segment in there. And there are different options for all those kind of separate modules. You know, each of those R's can be calculated in a different way. And so it's useful to know what your developer is using. You know, are they using a conservative model? Are they accounting for changes in rainfall? You know, are they using more recent data? Or are they using like an aggressive model and saying, oh yeah, no, you know, they're using data from 100 years ago, and so they're predicting very little runoff, right? But really, it's because they're not using a proper model. So I know, I'm sure it's challenging to get developers to tell you how they're doing their sizing, but you know, if they will tell you, you can use that information to get an estimate of, hey, what is this impact how is that going to impact me downstream? And now, you know, and some of these things that I brought up here, at least you can kind of challenge and say, hey, you know, have you considered this? Have you considered that? And maybe give you a better comfort level on the risk of from all the flow coming off that site.
Great, thank you.
You're
Right,
welcome.
thank you. Very good. Yes, indeed. That situation is, as I said, it's pervasive throughout the Caribbean region, and of course, as we have a rapid urbanization in some parts and urban drift, urban sprawl, as it were, you do get that type of situation arising. But I think, as you have demonstrated through this presentation, through the introduction of this subject, I think there are scientific ways to manage these situations, to be able to predict as best you can, and it will allow for proper and better management of flood situations, of stormwater. So at this stage, I think we've gone a little over time,
Oh, yeah.
and we appreciate your giving us all of that time this afternoon. So we'd like to thank you immensely, Dr. Williams, and we trust that sometime in the future we may be able to have another similar presentation from you. And we'd like to thank Valerie and the team. And I'd like to thank Sweeta Bihari of CWWA for assisting us in promoting the webinars on a Wednesday. And we'd like to thank all of you for joining us.
So
And we look,
Ignatius, they should definitely join in next week, because if you're an operator, this will be of great interest to you, because we have the region of Peel coming, one of Canada's larger regions, and they're going to be talking about challenges that they've had. Because even well-run utilities that have good resources can have some challenges. They're going to talk about some of their challenges and how they overcame them. So I think it'll be a great interest to your audience.
Thank you. So we're going to be sending the adverts out by the weekend, and so you get ready for the next presentation, webinar number 16. If it's Wednesday, it's CAWASA Wednesday webinar. I'm Ignace Jean, signing out. Thank you very much, Dr. Williams, and all
Thank
of you.
you.
Goodbye.
Thanks, everybody. Take care.
Have a good evening, everyone.